Professor for his idea to invite to our seminar Professor Chen. And with great pleasure, I would like to introduce the talk of Professor Chen, Nonlinear limit theorems for a set of probability measure. Please, Professor Chen, you have 1 hour. Please,
Okay.
you can.
Okay.
Lena, you forgot to ask to turn off the picture and the sound.
Yes,
Yeah.
exactly. We have a tradition. All participants can ask you during your talk, but during your talk, all our participants can turn off microphone and video. Thanks.
Okay.
Please start.
Okay. First of all, I want to thank the organizer for this opportunity to report some my work on about the nonlinear linear theory. Also, I want to thank my thanks Ulyanov and Stoyanov. Both of them is the bridge between the Moscow University and the Sanu University. When they with Sanu University, we learned a lot of things from them. Today, I want to talk a story about the nonlinear limit theory. This is a very very old topic. So, this talk is based this is work joint work with the Larry Epstein, who is the professor in Boston University, and another person is Zhang Guodong, is my former PhD student. This talk is based on the 4 papers. In this talk, I did not give the proof. I just want to give some idea and some formula. So if somebody like to study the proof, you can find the proof in these papers. One paper is publishing the SPA. Another is publishing the JET in economics, because Larry Epstein is one famous economist, and another paper is published in the statistic. So this topic have a lot of relation with the Russian mathematician. So in the world, everybody know Kovalov is the founder of the modern probability, because he gives his explanation. Because his great work, not the probability, have get a series achievement. This achievement is based on the 5 initial conditions of the Kovalov explanation. In the Kovalov explanation, he suppose the probability space have 1 probability. This probability is given. However, in real and certain case, such a probability measure usually is unknown. Usually in economics, some people said this is the probability. Usually is ambiguity. Some case the probability is one set. One don't know which one is best choice. For example, in mathematical finance, usually there are a lot of the probability measure, but the people don't know which one is a good one. So in this case, in finance, usually a lot of the model is invalidity Kovalov explanation. For example, in mathematical finance, one famous formula is called the Black-Scholes formula. The formula is is given in this form. He suppose in company markets, if you want to give the price of the option, black and shoes proof in company markets, there exists a unique neutral probability too, such that the price of the option can be represented by the expectation. So meaning is if the market is company markets, there exists unique probability. Then the price usually is probability is expectation. So how to calculate expectation? In probability theory, we have the law of larger number, and also we have the central limit theory to calculate the expectation. So this is why, in mathematical finance, most people can use the probability to calculate the price of the option. Unfortunately, if the market is in company markets, some people prove in this case, the probability measure is not unique, it's one set. We don't know which one is good. In that case, lot of people give the upper price and the summer price, use the upper expectation and the lower expectation. And also the probability, we can have the upper probability and the lower probability. So from this, in finance, the upper expectation and the lower expectation usually is nonlinear. So with some cases, we call the nonlinear expectation. The upper probability and the lower probability usually also is nonlinear. So some case we call the nonlinear probability. In this case, how to calculate the upper price and the summer price in finance? This is a very important question. Unfortunately, if we use the law of larger number and the central limit theory to calculate this, usually it's not good. So meaning is in finance, a lot of people want to calculate the upper price and the summer price. Meaning is how to calculate the nonlinear expectation. This is a question. So how to calculate the upper and the lower price? This is one question in finance. And some people also ask, is there law of larger number and the central limit and the nonlinear probability? So this is the second question. In probability, we have the normal distribution. So the third question is, can we get the closed form of the distance function in under the nonlinear calculation and the nonlinear probability case? This is in mathematical finance, this is a very important problem we should to overcome. So you how to calculate the nonlinear calculation is our main topic in this talk. So as you know, the central limit theory is most result is from the Russian mathematician. Okay, I read one book that there's for the central limit, there are 3 stages. Okay, something like this. I guess Russian people know this. These people is from Russian mathematician. But in the probability for the law of larger number is usually from the Bernoulli model. From the Bernoulli model, give the central limit theory, and then Gauss studies the error distribution. He gets the normal distribution. So now we call some case we call the Gaussian distribution. And also common law give the more general case, give a lot of the result. But the meaning is this random, if the in ID case, this term converges the normal distribution. This is a universality. Okay. So meaning is if the random variable is ID with the finite mean and the variance, in that case, this statistic converges normal. So this is a normal distribution. So meaning is this function is very beautiful, have one pit. So the question is, if the random is not AAD, can we still get the result or not? For example, if you know in probability, one important definition is independence. This given by the de Wolf. He used the conditional probability to define the independence. So in that case, if we extend the probability space for one probability to the set of probability, and we use upper and lower probability to study the central limit theory, how can we get? You know, in from this guy, he said, usually when we study probability, we suppose the probability is a linear case, but usually some case, this probability is not is a nonlinear case. For example, upper expectation, upper probability and the lower probability is nonlinear. So now we want to study the two questions. If the probability is nonlinear, but the random is non-independence, how to study the law of large number and the central limit theory? For example, we recalled briefly about the Bernoulli model. For the Bernoulli model, he said repeat independent trio is called Bernoulli models. If there are only two possible outcomes for each trio, and their probability remains the same through the trio. Meaning is usually we use a coin model and the arm model to represent the Bernoulli model. In fact, we can use the one arm slot motion to represent the Bernoulli model. So now if you know the two-armed bonding is said, suppose one slow motion with two arms, drawn ball with the black and the red color. Reward of each arm is with distribution F1 and F2. The distribution is different with the different probability measure. How should we draw a sample? Use the two arm if our object is to achieve the greatest possible expected value of the sum. How to calculate this? In that case, the probability, we have two probability. The probability is not unique. In that case, we want to get the distribution of Sn and the capital V and the small v. So this is nonlinear case. So in order to solve this question, we translate this to the probability space from one arm to two arm, one arm banded to two arm banded. This is something like this. In that case, the probability in this, for example, this arm have the different distribution. The two arm have the different distribution. Okay, in that case, we want to discuss it. So we call this the binary ascendant Bernoulli model. So we have the two arm, but each arm have the different distribution. has drawn the boy from the two arm such that the reward is best good. So if I use the binary uncertainty model, we use this. For the binomial model, we suppose for each time we have two outcome. But for this model, each time not only have two outcome, but we have two distribution. So we call this a binary uncertainty model. Okay, each time we have two outcome and we have the two distribution. From this, we want to get the law of large and central limit theory. So recall briefly about the method of the proof for the central limit. You know, lots of people prove the central limit theory and the law of large number. For example, Bernoulli proof use the study the special case. Okay, Lindenberger uses the same group to prove central limit, and Levy uses the characteristic function to prove this, and also Steven uses the Steven method to prove central limit. But the China mathematician Peng used PD to prove this. But I wish Larry Epstein use the BSDE, backwards stochastic deflation equation to prove this result. Okay. How to prove the result of central limit and the law of large number? You know, in the class case, we consider two statistics. One is the law of large number. This part is law of large number, but this part is central limit. But we study in the probability theory, we usually prove the central limit and the law of large number separately. For example, we can compare both if these together. If P is unique, we have this law of large number and the central limit theory. Be careful in the for the expectation UP. Usually, this expectation depends on the P, and also values depend on the P. So meaning is if the probability is not unique, is one set. How can we get the law of large number and the central limit? For example, we want to discuss what is the distribution of this and the upper probability. But here we use the condition expectation because in this case, random usually is not independent. So my question is, how can we get the distribution for this, for any x and y, and the upper probability? This sum this. So now we want to give the some assumption. For example, if we give one set of the probability, some people define the stable probability measure set. For example, this guy defines this, and thereby he also defined what is the set, what is stable probability measured. He defined, suppose one set of this, one set of probability, satisfy the equivalent stability composition, stability of bifurcation. He gives a definition. For example, we give one set of probability. We give some condition. This guy gives this condition. In this talk, we use this definition for the set of probability, and we also give the conditional conditional expectation and the law conditional occupation. Meaning is the mean and variance satisfy this, and this is the variance, upper variance and the lower variance. Okay, we give this condition. And also we still use the Lindenberg condition. We use this, just we use the upper expectation like this. Use this, we can get the law of large number. For example, yeah, first we get one result. Suppose the set of the probability is stable. We suppose the random variable satisfies the condition B1 and B2. Okay, B1 and B2 is this is the B1 and B2 satisfy this condition. In that case, we define this term is the sum of the sample. This usually we call the volatility. This is the errors for this. We consider the both of the statistic. We define for any function, two dimension. Okay, this term, this is the center, this is the mean, this is the volatility. We can prove, and this the upper expectation convergence this. This term is the Eaton integral. This BS is Blow motion. And the lower expectation converging into this. But this set is the rectangle. This upper the lower expectation, upper expectation, lower variance, and the upper variance. So in that case, the joint distribution Sn and Sn2 converges this term. This depends on the mu. Okay, this one result. In that case, we prove this term usually is law of large number. This term is central limit. We prove this both these together. This is a more general case. So meaning is this term is Blow motion. This term is Riemann integral. So the next question: can we get the closed form for if the u is index function? So if we now we consider special case. If the u is a two dimension, okay. If the function u depends only on x on y, just depends x or on y. This term the result the theory becomes this. This is the mean sample mean convergence this term. Usually we can call this law of large number upper and lower expectation. But we can also, if the mu is an index function, we can guess the law of large number with the upper probability. Meaning is the sample mean convergence for any mu for any b in this interval. This convergence with probability 1, upper probability. This lower probability. Meaning is in this case, the sample mean located in the interval, this and lower probability. So from the general limit theory, we can get the law of large number theory. In that case, we have usually we call the weak law of large number. We can get this form. And if we consider the central limit, okay, if we consider Sn2, we can get this convergence is integral and upper expectation. And lower expectation, this term convergence, this is the if somebody knows Martingale, this convergence in this. But if the mu is index function, we can get the distribution function in this form. Okay, the two, this convergence, this is the closed. We can get the closed form. Okay, now we can get the limit. We can get the limit law of larger number and central limit. If we can get this form. Next, we want to get the more special case. We suppose if the mean is an uncertainty, but the variance is not an uncertainty, we can get the closed form. We can get this term, this law of larger number, this term plus this term convergence this. This is a solution of the BSDE, because you know in Shandong University I work the BSDE. So we can solve this BSDE. We can get the closed form. So this BSDE special case is in this form. So we can get the solution is in this form. But we can get this if this index function, we can get this form. But this but the function is not beautiful. But we can write in this form. We can get the data function is this is in this form. If under the upper probability, the distribution is in this form. This is the distance of the statistic and the upper probability. So this is we usually call this spec distribution. But here this term is normal distribution. So under the upper probability, the distribution function is in this form. But under the lower probability, the distribution is a binomial distribution, is in this form. This function can be drawn in the picture of the picture of this function is in this form. So meaning is if the mean is uncertainty, variance is not uncertainty, the distribution of the random variable is in this form or in this form. So in this form, we have two peaks. But the normal distribution usually have one peaks because the normal distribution is AAD. But now we have the two and is not identical. So in that case, we have the two peaks. So this is the distribute function and the upper probability and the lower probability. So the phi is the normal distribution function. Okay, we can get the form of this. Okay. The next is if we suppose mean is not uncertainty, but variance is uncertainty. In that case, we can get the density function is in this form, and the upper probability, expectation, the density function is in this form. The density function is in this form. It's not symmetric, but in this set is in this form. This set in this form. But if we use the lower probability, the form is in this form. It's the form. Okay. If the variance is the same, upper variance equal the lower variance, This is normal distribution. Normal distribution. So now we prove if the mean is not an insanity, variance is insanity, we get the closed form. If the mean is not an insanity, variance is not an insanity, we also can get the closed form. In that case, we can see if variance, upper variance and lower variance is not the same, the distribution function is not normal distribution, it's not symmetric. Okay. The third case, we consider both mean and both mean and variance is insanity. In this case, we consider this special case. We can also get the closed form of the density function, but under this case, okay, usually we cannot get the closed form, but for that case, we get the density function. This function is in this form. It's very complicated. It's very complicated in this. But if I draw the picture, it's in this form. Special case. This is the variance. This line with this line, where is density function. This line with this line is density function. This line with this line. So meaning is in that case, we have the two peaks. So this is our result that we get. So this means we prove the central limit theory. Central limit theory, a law of large number. So next, I want to give the application in statistics. So in statistics, usually we have the very important topic is hypothesis test. Usually we suppose original is H0 is mu1 equals mu2, whereas mu1 is not mu2. So probability theory is very good for this topic. But use the nonlinear case, we can consider that by similarity. Original subset text is mu not equal to 2. If we suppose mu1 is not equal to 2, meaning is we have upper expectation and lower expectation. If we know upper expectation and lower expectation, we have the density function. So in that case, we can use the abort result to do hypothesis test. Okay, this is one application. The second application is Monte Carlo method. You know, Monte Carlo method is very good to calculate the integral. But follow our law of larger number and the nonlinear case, we can calculate the maximum value plot. Meaning is we can calculate the optimal values. So meaning is we can use to calculate this term. So meaning is for the nonlinear case, we can if we see the linear case can calculate the integral, but for the nonlinear case, we can calculate the optimal values. This is the some kind of application. The third application is, for the PDE. For the PDE, the solution, we can use the limit theory to represent the value of this PDE. Meaning is we can use the law of larger number and the central limit theory both together to calculate the solution, the value of the PDE, TVDE. Yeah, this is I want to say. For the nonlinear case, we still can use the nonlinear limit theory to study the statistic and to study PDE. So finally, I want to say, in the probability theory, usually we suppose the random is IID. So in this case, the distance function have only one peak. Only one peak. Without the IID, for example, non-IID, usually the distance function have more than one peak. In case. So for the nonlinear case, usually the random variable is not IID. So the other things I want to say, if we see the probability is from the gambling with the one-arm banded problem, then we can see nonlinear probability maybe it can be solved from the two-arm banded problem. So in that case, you know, if we consider the nonlinear probability, so with the very classical model, maybe it's a two-arm banded problem. So this is I want to say, okay. Okay, this is all I want to say. I want to talk. Thank you. Okay.
Thank you very much. Professor
Okay.
Yarovaya, are you here now? Could you?
Yeah, I saw.
There is some technical difficulties again, so maybe.
Which one?
Okay, thank you very much for your talk.
Okay, thank you.
We are ready for some questions about the talk
Okay.
now. Does
Okay,
anyone
thank you.
want to ask it?
Okay. Oh, maybe I have.
Or maybe some commentaries?
Oh, yeah.
Okay, maybe I shall start. So, Professor Chen, thank you very much for a very interesting talk and very clear presentation.
Thank you.
And so, one remark and one question. So, in the talk, it was considered two basic results of probability theory: law of large numbers and central limit theory. And we have seen how situation becomes much more difficult if in probability space we replace one probability by two probabilities. So this is the model of two-arm bandit. And in fact, there are also another papers in this direction, but what is important for results which Professor Chen presented, that limit distribution in these results is given in closed form. This is very important because in many papers, it's not clear what is limit distribution. It's described like solution of some PDA or something else, but now we have result in closed form. And one question for you, Professor Chen.
Okay.
So as I understand, this is one of the first steps in this direction, in this field, because you don't give rate of convergence. So you give only limit distribution, but it's not clear how fast we come to this limit distribution, right?
Yeah.
So maybe this is the future direction of your research.
Mm.
Thank you.
Okay, thank you. So what is your question?
No, my question is that, as I understand, you give convergence to limit distribution, and you describe limit distribution in closed form, but you don't give how fast this convergence you have.
Oh, yeah, okay. So it's a very good question. How to give the speed of the convergence? But I try to calculate this, but no, still I have no idea how to calculate this. This still is an open question that maybe I can to prove in the future. Okay.
Thank you.
Professor Ulyanov, I think it's too difficult question from you. Please comments, maybe. Excuse me, please. First of all, I have today a problem with internet connection, but maybe in other comments, please.
Lena, it seems Albert Nikolaevich Shiryaev wanted to tell something, but he didn't turn on the sound.
We ask him, Альберт Николаевич, вы с нами? Вы нас слышите? Альберт Николаевич, вы звук не включили, поэтому мы вас не слышим.
Это
Нет, он включен, но мы
заметили...
почему-то не слышим.
Слышно? Сейчас слышно?
Да,
Сейчас...
Альберт Николаевич, но мы ничего не слышали, что вы говорили до того. Поэтому просим...
сейчас слышно?
Сейчас отлично слышно. Спасибо.
Professor Chen, show please formula number 4. Please show formula number 4.
So it's not clear, but how?
No, 4.
Oh,
Another direction.
this one?
Yes. Show. In this formula, you assume that conditional expectation random variable xy with respect to any measure q does exist. Yes?
Yeah, this is so that's key. Sorry.
No, and so in for definition of your random variable s and q.
Okay, S and Q, yeah.
You assume, of course, that expectation with respect to measure q, x, y, that does exist. Correct.
Yeah, this case usually because the random variable xi is not independent.
Yes, but what I want to say.
Yeah.
Of course, it's very interesting to consider your theory for case then we have no expectations. From this point of view, please look Kolmogorov Foundation of Probability, chapter 6, paragraph 4.
Okay.
Where he considered law of large number not under uncertainty for one measure, but he doesn't assume existence of the expectations. And so your theory should be expanded to the case then for each measure q we have no expectation. So simply I want to say I am thinking about extension of your work, and I know, in fact, your work of the Louis Shige, Peng, and so on. But it is interesting, of course, to consider the case of law of large numbers center limit theorem under assumption that no condition, no expectation.
You
Yeah, okay.
assume this one. You assume this one, but next there is next step. And for this case, I want to say, please look Kolmogorov chapter number 6, and paragraph 4 and 5. Все, Лена, я кончил. Я могу по-русски сказать. I would like to repeat everything in Russian. Вообще во всей этой теории, которая рассказывалась, там есть предположение о существовании математических ожиданий. Но представьте себе, вы хотите закон больших чисел получить для случая, когда математические ожидания не существует. И он существует. И Колмогоров в своей аксиоматике 33-го года это дело написал. Так что я просто хочу сказать, что следующий шаг вот в этой работе, которую нам сегодня рассказывал, состоит в том, все рассматривается в предположении многих мер, то есть предположение uncertainty. Это надо, конечно, бы делать и дальше. Это хорошая тема для следующего. And so, Professor Chen, it would be interesting if you, besides of the two-arm bandit problem, to say about paradox Allais and Ellsberg. You know, of course, paradox Allais and Ellsberg, which contradict to the von Neumann theory and the theory of Savage and so on. Я как-то об этом говорил. Может быть, не все поняли, что вот парадоксы Аллея и Эльсберга, они тоже относятся вот к этой тематике, и они противоречат. И они придуманы были для того, чтобы показать, что теория фон Ноймана, Моргенштерна и теория Сэвиджа не всегда верна. То есть реальные люди, реальный человек поступает иногда не так, как диктует эта теория. Ну, все, это я по-русски сказал.
Okay, thank you.
So maybe,
Thank you for your comments. Professor Ulyanov, please.
yes, Альберт Николаевич, maybe I start from Russian and then I translate. В защиту, ну не в защиту, а просто в замечание. Парадокс Эльсберга обсуждается в работах Чена на самом деле.
Да я знаю, нет. Я хотел сказать, что он приводил примеры бандиты и прочее. Надо было сказать еще. И он, конечно, я знаю, что он знает. Что надо было бы сказать о парадоксе Аллея и Эльсберга. Просто, это мы уже об этом говорили. Поэтому немножко жалко, что он это не сказал. Поэтому люди могут не сопоставить вообще всю эту науку.
Ну да. Нет, Эльсберг, конечно, интересно. То есть поведение людей отличается от того, что говорит классическая теория.
Нет, конечно, они отличаются классической теорией, и, конечно, с помощью capacity of, capacity это все преодолевается и прочее. Это уж я просто скажу. Скоро должна выйти моя книжка, вторая часть «Бронское движение». Там в 36 главе об этом написано.
Спасибо. Professor Chen, we discussed slightly Ellsberg paradox.
Okay.
Нет, мы его запутаем только. Не надо, давайте уж лучше об его докладе задавайте вопросы.
Конечно, other questions?
Of course, the question about the how to say, the rate of convergence is very complicated here. It's definitively, it's not very simple case.
However, there are results by Professor Penn and Shao, who received rate of convergence under another frame.
Yeah, Peng have this result about the PDE. Okay.
Yes.
Yeah, this is the Peng's result. Yeah, similar like this, the PDE.
Yes.
Вот в этой, я по-русски скажу, в этой формуле последней, вот есть SNQ, но оно может, представьте себе, что оно не существует, потому что оно определяется через, ну, там, условное математическое ожидание, а их ведь нет.
Но у него основной...
теорема-то нужна.
Нет, вопрос справедливый, но в случае бандитов, двухруких бандитов, там существует.
Ну ладно, это мы вступаем, не надо быть вежливым гостю.
Yes.
Можно об этом не говорить.
Dear colleagues, maybe in other comments, if not, we would like to thank Professor Chen and maybe to invite you, Professor Chen, to give another talk on our seminar next year, maybe with new results. So we will be very glad to see you again. And now I would like to give announce to our another talk. Our another talk will be, please note, 15th of May, because we have holidays of 1st of May and short day 5th of May. So our next seminar will be 15th of May. And we will have a talk of Sergei Novak from England on t-test. Он из Англии, Миддлсекский университет, Сергей Новак.
Сергей Новак из Новосибирск.
Вот именно.
Но аффилиацию написал себе такую, поэтому...
Нет, но это сейчас он там. На самом деле происхождение из Новосибирска, конечно.
Конечно, но вот...
I didn't understand the title, so again, can you repeat it?
Очень просто.
По-русски скажи, пожалуйста.
О Т-тесте. Я так понимаю, он будет обсуждать вот стандартный Т-тест. Условия его применения, что не всегда он применяется грамотно и так далее. Я думаю, что об этом будет доклад. Вот. Очень простое название. О Т-тесте.
Понятно.
Вот. Поэтому, уважаемые коллеги, встречаемся 15 мая. К сожалению, вот у нас тут праздники попали. Вот. Поэтому до 15 мая. Да. К сожалению. Устали от большого семинара.
Лена, я еще раз скажу. Профессор Чен, in fact, we know very well your works. And we, at least myself, I'm looking all China's works in new direction about uncertainty measures and so on. In fact, you are doing very good job, and it is new direction. It is new direction. It's necessary to do it. It's very pity, but in our country, not too many people who are working in this direction. But in any case, I think that together with our Chinese friends, we also will start to work in this area actively. Thank you very much.
Okay, thank you. Yeah, thank you. Yeah, you are.
And please do my best regards to the Xi Jinping.
Okay, yeah, I will see tomorrow.
Good friend Xi Jinping. Thank
Yeah.
you.
Okay, thank you. Yeah, I will see Professor Peng tomorrow. Yeah.
Тогда на сегодня мы заканчиваем. У нас будут, я сразу хочу сказать о расписании. У нас будет семинар 15 мая и 22 мая. Потом мы уже встретимся осенью. Еще 2 семинара у нас будут.
Да, но у нас еще будет конференция в Дивноморске в начале июня. И
да,
как назначенный председатель оргкомитета и программного комитета, я приглашаю всех участвовать в этой конференции. Я надеюсь, что это будет интересно. Это 9-я конференция, ну а в следующем году, я надеюсь, будет 10-я.
Альберт Николаевич, я хочу немножко дополнить, что продлен дедлайн для тезисов до 25 мая, и поэтому есть вполне еще возможность представить тезисы и доклады на эту конференцию в Дивноморском, которая состоится со 2 по 8 июня.
И чем позже вы подаете свою заявку, тем позже поставить ваш доклад. Ничего не сделаешь. Люди уже прислали доклад, мы уже сформировали часть программы, потому что мы не знаем, будут ли еще дополнительные доклады или нет, но начальные доклады уже составлены. Начальные доклады составлены. Ну и я хочу сказать, что вообще первый доклад там будет делаться, по-видимому, мною, потому что этот год 300-летия Академии наук. Я расскажу кое-что о Петре Первом, Екатерине и так далее. Все,
дорогие коллеги, тогда мы заканчиваем. Профессор Chen, we will wait for you in our seminar, maybe next year or this year. Thank you once more, and we finish our conference, our seminar. Thank you.
Thank you.
Okay, thank you very much. Bye-bye.
Thank you.